Hi everyone, welcome back. In this video, we will learn about hydrogen bonding. Hydrogen bonding is a super dipole-dipole force. It involves polar molecules just like the dipole-dipole intermolecular force we were discussing in the previous video. But it mainly works with polar molecules that also have an NH bond, OH, or FH. They are stronger than dispersion and dipole-dipole intermolecular forces, and the strength depends on the number of hydrogen bonds between molecules. So some molecules can have 2 hydrogen bonding interactions, or 3 hydrogen bonding interactions, as we'll see in a video we'll watch at the end on the structure of DNA. The strength of a hydrogen bonding interaction is also dependent on the size of the molecule, as we've seen with dispersion intermolecular forces and dipole-dipole intermolecular forces. Something I want to emphasize here again and again is that it's not a covalent bond. Unfortunately, it's a misnomer. When students hear hydrogen bond, they think it's an actual bond. But just like all the other intermolecular forces that we have learned so far, it's only an interaction. So it's an interaction between 2 or more molecules. So let's see how that's, represented here. So we're looking at hydrogen fluoride. So that would be this atom here, and then hydrogen over here. And remember, fluorine's the most electronegative atom on the periodic table, and so it's very much a partial negative, very electron rich, and the hydrogen is therefore electron poor because the fluorine is just hogging all the electrons towards itself. And because of this, if you have these bonds present, then the bonding atoms acquire relatively large partial charges, right? So their permanent dipoles are pretty strong here, right? Like the charge separation is apparent between the hydrogen and the fluorine. Same goes if you had hydrogen, oxygen, hydrogen, nitrogen, right? And because of that, that means that this dipole-dipole intermolecular force is a very strong force. And in fact, that's why it's distinguished as hydrogen bonding. You can also see this hydrogen bonding interaction represented using the electrostatic potential map. And, this particular map here, you definitely see the red region and the blue region. It's very distinct. Whereas in the previous video, when I showed you the electrostatic potential map of acetone, the red and blue were not as distinct as they are here with the hydrogen fluoride. Let's look at another example here. This is ethanol, and the structural formula here, it's 2 carbons, right? And then an OH attached, right? And ethanol can only participate in 1 hydrogen bonding interaction at a time. And if we were to assign where the permanent dipole moment is within each molecule, remember oxygen is more electronegative than carbon and hydrogen. Now, the carbon directly attached to the oxygen is also partial positive. that oxygen is pulling electron density away from the carbon as well. But the interaction that's really taking place here, the most dominant one is the hydrogen bonding, because there's definitely a larger difference in charge separation between a hydrogen and oxygen than between an oxygen and a carbon. Okay. And so here's how you would represent the hydrogen bonding interaction. And just be careful. I've seen students want to draw solid lines, or students will say, oh, it has an OH bond, and therefore that's the hydrogen bond. No, that hydrogen bonding is the interaction. It needs to be that dot, dot, dot between two or more molecules. And you can see it in the space filling model here. It's showing the partial negative of this oxygen really interacting with the partial positive of that hydrogen. And then the electrostatic potential maps once again, the very red oxygen really interacting with the blue partial positive hydrogen of another molecule. Now, sometimes I'll have students ask me, are these hydrogens, or is these oxygens interacting with these carbons? I mean, that's technically also taking place. But the stronger interactions are really what's going to dominate and determine the properties of those molecules. Okay. Wanted to show you another example with data. So we're looking at propane, dimethyl ether, and ethanol, right? And I'm going to write down their molar masses. So the molar mass of propane is 44.09 grams per mole. For dimethyl ether is 46.07 grams per mole. And for ethanol is 46.02. And so it's really important, if we are looking at molecules that have different intermolecular forces, that we're keeping the molar mass the same. Now, if we're looking at molecules that are all dispersion forces, then it's okay to change the molar mass as a variable to see how molar mass affects the strength of the intermolecular force and therefore the properties. So in this case, these won't all have the same intermolecular forces, and so it's important for comparison's sake that we keep that molar mass as a constant variable. Now, if we look up this data here, the boiling point is negative 42 degrees Celsius for propane, which makes sense. It's a gas at room temperature. Dimethyl ether is negative 22 degrees Celsius, and ethanol is 78.3 degrees Celsius as its boiling point. So therefore, the phase at room temperature, as I said, this is a gas. This is also a gas, because remember, room temperature is 25 degrees Celsius, but this ethanol is a liquid. And so even though they have the same molar mass, something else is coming into play to give each of these molecules like their own unique phase at room temperature. And it all comes down to intermolecular forces, right? And so what's the strongest intermolecular force for propane? Okay, it's dispersion because it's a nonpolar molecule. Excellent. What about for dimethyl ether? Okay, hopefully you said dipole. And we just said for ethanol it was hydrogen bonding. And so therefore, because ethanol has the strongest intermolecular force, it has the highest boiling point, and that's why it's a liquid at room temperature, whereas dimethyl ether and propane are not. Now, just one final comment regarding this data set. Sometimes students ask me the question like, well, I don't understand. This one had an oxygen in it, and it has hydrogens in it too as well. Why does dimethyl ether not participate in, I promise that's a hydrogen here. Why does that not participate in hydrogen bonding, right? And the issue here is that the hydrogen needs to be directly connected to an oxygen, nitrogen, or fluorine for hydrogen bonding to take place. The fact that these hydrogens are actually attached to a carbon means that they are non-polar hydrogens. They're actually not even partial positive, because in a non-polar covalent bond, electrons are evenly distributed. And so they're not even really interested in interacting with that oxygen all that too much. So that's why we only have a dipole-dipole interaction that's between oxygen and carbon. And so that interaction would take place, but would not be as strong as something like ethanol would experience with the hydrogen bonding. So the hydrogens need to be directly connected to oxygen, nitrogen, or fluorine for hydrogen bonding to occur between many molecules. Okay. All right, I wanted to end with a video showing the structure of DNA. So many of you may have already taken some biology and you've learned about DNA in your classes, and you probably have heard of the phrase hydrogen bonding before, that term. And now I just want to tie that all in together, right? Having this knowledge and building this foundation of intermolecular forces will not only help you in my course, but will help you in future courses.
Do you recognize this molecule? This is DNA, or deoxyribonucleic acid. By the end of this video, you will be able to identify the key structural features of DNA, as well as describe the importance of those features for function. During this video, we will look at different representations of the DNA molecule to better view certain details, but all views represent this same structure. Inside the cell, you will most commonly find double-stranded DNA, in which two strands intertwine to form a double helix. The most common form of the DNA double helix, which is what we will discuss here, is also called B-form DNA. Now, let's move to a more simplified representation of DNA to discuss the details. We can unwind the double helix like this, so that we can see the chemical structure inside. Each strand is a polynucleotide, meaning the strand is made up of many individual units called nucleotides. A nucleotide has three components: the 5-carbon sugar, a phosphate group, and one of 4 possible nitrogenous bases: adenine, guanine, thymine, and cytosine. The nitrogenous base is always attached at the 1' carbon of the sugar. If we count from there, we can see that there is a phosphate between the 5' carbon of one sugar and the 3' carbon of the neighboring sugar. The sugar is called deoxyribose because it is missing a hydroxyl group at the 2' carbon, which is present in ribose. Because of this, nucleotides in DNA, deoxyribonucleic acid, are called deoxynucleotides. Nucleotides attach to each other in the DNA strand by phosphodiester bonds. The phosphate group of one nucleotide binds to the 3' oxygen of the neighboring nucleotide. Thus, we can see that the sugars and phosphate groups make up the DNA backbone. The carbon numbering is key to describing the directionality of the DNA strand, 5' to 3'. Looking within the sugars, there is an intrinsic orientation difference between the two strands. On the top strand, you can see that the 5' carbon of each sugar is on the left, and the 3' carbon is on the right. The opposite is true for the bottom strand. Reading left to right, that makes the top strand orientation 5' to 3', and the bottom strand orientation 3' to 5'. These strands are also sometimes called Watson and Crick. Keep in mind that this double-stranded DNA is still a double helix, and we have simplified the representation by flattening and unwinding the helix here to better see the atomic structure. Although the nucleotides come together through covalent bonds in the backbone, the two DNA strands interact through non-covalent hydrogen bonds between the bases. Each base forms multiple hydrogen bonds with its complementary base on the opposite strand. Bound together by hydrogen bonds, Each unit is called a base pair. The hydrogen bonding contributes to the specificity of base pairing. Thymine preferentially pairs with adenine through 2 hydrogen bonds, and cytosine preferentially pairs with guanine through 3 hydrogen bonds. Thymine and cytosine are called pyrimidines, characterized by their single ring structure, and adenine and guanine are called purines, which have double rings. The geometry of the AT or TA and GC or CG base pairs is the same, allowing for symmetry and base stacking in the helix. This mostly has to do with the distance between the backbones and the angles to which the bases attach to the backbone. Other base pairs, like GT for example, do not have the same geometry, cannot form strong hydrogen bonds, and disturb the helix. The double helix structure of DNA is highly regular. Each turn of the helix measures approximately 10 base pairs. In addition to the hydrogen bonding between the bases, the stacking of the bases also stabilizes the double helix structure. These pi-pi interactions form when the aromatic rings of the bases stack next to each other and share electron probabilities. The regularity of the helical structure forms 2 repeating and alternating spaces called the major and minor grooves. These grooves act as base pair recognition and binding sites for proteins. The major groove contains base pair specific information, while the minor groove is largely base pair nonspecific. This is because of the patterns of hydrogen bond acceptors and donors that proteins can interact with in the grooves. In this way, the DNA can be acted upon in either a sequence-specific or non-sequence-specific manner, allowing proteins to position themselves correctly in the genome to carry out their designated tasks. This is the DNA double helix, and you've now learned the structural features that influence its function. We hope you've enjoyed exploring this amazing molecule with us.
All right. So, thank you for watching, and I will see you next time.